accept the reality of the world with which we're presented. It's as simple as that.
All right, hello and welcome to GLOBEBUSTERS, Season 13, Episode 13. Today's subject is ether physics. But before we get into that, let me introduce the panel and give a special shout out to Cami, who is continuing the platform in honor of Bob's legacy. If you want to support the channel, all proceeds go directly to Cami. You can do so by super chatting or becoming a channel member. And anything super chatted, we will read live towards the end of the show. Or any questions you have, you can ask via super chat, and we'll be sure to read those. Starting off with Zack. Hello, sir. Welcome.
Alan, what's going on, brother? How was your week?
Fantastic. Another glorious week.
Yeah, there were some storms that rolled through. Did you guys hear about that earthquake?
Never met her.
Oh, I think it was in Thailand. 7.7, like buildings just crumbling down and stuff. Like
Dang.
big, crazy earthquake. Yeah. So lots of love to all the people out there who, might be being affected by Mother Nature this week. Yeah. Lots of love and prayers out to you all. That's one thing I don't think we're ever going to get a grasp on is, containing Mother Nature. I think we try and then it laughs and says, haha, try this.
Oh, you want to build a city here? That's cool. Build a new one. And we got Shane, of course. Scale and Ether Cosmology. What's up, Shane?
What up, fellas? What's going on, everyone? Good to be here. Yeah, man. You think that we can't control the weather? I mean, we geoengineering. They still, I'm pretty sure, use HARP for earthquakes. So we have to look into that particular one to see what was going on with the placement or whatever country was trying to get a new World Bank or whatever.
Yeah, wasn't it Tesla who said he gave him enough power he could split the Earth in half? He said.
Was Thailand trying to get off of oil money or whatever?
I guess there's probably a story there.
All right, cool. All right, so we will get into the ether physics prezi here. It should run about an hour and a half-ish, maybe.
Dude, this is one of my favorites. And I don't know if you saw, Alan, but the GLOBEBUSTERS Tech did on Thursday Ether. What is the Ether, I think?
Ooh.
So this is a nice kind of rolling right into this, I think. It was a nice precursor. I think they covered the etheric framework, how to interpret, electromagnetic phenomenon via waves, particles, the whole thing.
Nice,
Yeah.
dude. The extended version. I know, dude. Yeah. Isn't that awesome? It's like you could do all that. That's just touching it a little bit. You're just getting in there.
That's so awesome. This next Thursday is going to be a continuum of that because we just scratched like 2 small tiny videos of a plethora that we want to share with people.
Are we about to do a massive ether prezi?
Hey, you guys are more than welcome to come and hang out. You always know that. Yeah.
Oh, dude.
If you guys aren't doing anything Thursday night and you want to come, talk some ether with us. Yeah, we'd love to have you.
Are you talking chain ether prezis?
Chain ether prezis. That's awesome, dude. All right, cool. So we'll go ahead and get into this. But no, I did not see the episode, but it is on the playlist for watch later. I saw you got an episode on that. That's awesome that you covered all that.
Loving the weather here in South Carolina. Got to say it. Just already got peas sprouting, a couple inches tall. All the berries have blooms. We already have strawberries starting. Yeah, it's amazing. Like this didn't happen up north. I used to be at 41 degrees north up by Chicago, and like May 1st, May 11th, you would plant and you would, you'd be praying and hoping that there wasn't another frost coming. So yeah, it's just awesome down here. I love it.
All right. So ether physics. GLOBEBUSTERS presentation for season 13, episode 13. We're going to go answering the age-old question, what is the ether? We're going to define it. So starting with a framework of interpretation a mathematical reference frame to use that all motion will be relative to. And then also it'll be a physical medium with measurable properties, and it'll be the medium that is necessary for electromagnetic wave propagation to exist. You have no medium, then what is waving, right? We get into the classic logical antecedent relationship there, and we can logically deduce the need for a medium if something is going to be waving. So as we continue on here, we'll go through a line of logic in a null hypothesis situation. So we have our null hypothesis will be that the ether does not exist. Hypothesis that there does exist. So following from logical deduction, what exists in a vacuum? Is it nothing or something? We've all heard of 0-point energy, vacuum energy, quantum fluctuations, quantum mystery foam, like all these things that happen in a vacuum that apparently a vacuum has energy. Where does it come from? What does that mean exactly? What are they trying to do with it? Well, in modern times, through quantum, they explain this as a mathematical abstraction. They literally explain it through interacting, fluctuating fields of mathematics, guys. So if you're not into fluctuating fields of mathematics as the cause of the energy reading in reality, and you want something more physical, then we could look at the vacuum properties of electric permittivity and magnetic permeability, which we'll cover as we continue on. But supposedly, when you have a vacuum, you can make measurements of these properties of physical impedance, things that cause electric impedance and things that monitor or that would dictate the magnetic flux rate. So how fast electromagnetic induction can take place in a vacuum. There's something in there that has a limit to it. And so we'll get into the history of all that. So here's a little logical preface. So either there is something or nothing. Since nothing cannot have existence, there must be some form of reality. Something could be material, immaterial, or perhaps a combination of both, but existence of something in some form is undeniable. So if we have something in a vacuum that causes electric and magnetic impedance, we can't very well deny that there is something there. Any questions so far? The line of logical deduction there.
No, I like that. There are a lot of biblical, cosmologists, and before there was anything, there was the void. And it says it was, a vast expanse of some kind of liquid. And I'm not too sure that that's not wrong. Like above our head,
Right?
It makes a lot more sense that it's some super cool gas, getting further away from the source of heat. I still think the source of heat comes from below. That's what everything kind of tells me almost.
It's funny you mentioned liquids because light will be shown to have a hydrodynamic response, which maybe we'll cover at the end if the Prezi doesn't run too long. It's pretty interesting. You can make hydrodynamic predictions with how you can measure light, indicating that there's some fluid medium that might be influencing its propagation.
Just saying.
All right. So following this out, so if there's nothing in a vacuum, and we're not going to say that there's nothing in there because nothing exists, then we'll examine the physical properties of the vacuum, which are the electric permittivity constant and the magnetic permeability constant. Get into those now, and that's unfortunate that it's a little hard to read based on the slide there. But basically, we have the electric permittivity constant, which offers, like I said earlier, electrical impedance. So that affects how the conductivity, essentially, right? Like how fast electric can go through it. So we can think of that as capacitance as well. And then that's measured in farads per meter. And that'll be important later when we get into mathematical prediction for what the speed of light is. We've all heard the speed of light, rate of propagation, all these things. What does it mean exactly? Well, we'll get into what they're derived from here as we continue. So here are the values written out for the vacuum properties for electrical permittivity. comes out to 8.845 times 10 to the minus 12. And then for magnetic permeability, so again, this is in regards to, it would dictate the magnetic field flux, like how much it can change over time. So the inductance rate. So here we have 1.256637016 times 10 to the minus 6, and that's measured in farads meter. Or not, I'm sorry, that's in henries. Copy paste from that, but forgot to change the unit there. That's actually measured in henries.
What is a Henry?
The the magnetic permeability.
Okay, that's a new one to me.
Yeah, you can check out the SI unit. That's actually what we're gonna go over now. So when we're looking at how we've all heard that Maxwell, found that the speed of light is, close to 300 million meters per second. And he derived it from the vacuum constant. Well, what does that look like? What does that mean? So when we take the SI units for constants here for electric permittivity and permeability, we get down to seconds squared over meters squared. And we need to, so I'm going to go over the process on how we get to that, where we get to what Maxwell did at the end to find the reciprocal, using the reciprocal to show the speed of light. So here we're just going over the SI units that represent what these values are in terms of kilogram, like in terms of newtons, right? In terms of like how much force or whatever, coulombs and joules. That's what the units are going to be broken down to. And then when we get into the algebraic shuffling type thing, which we learned about, we did the Kepler and Newton dynamics episode, all we're doing is looking for things that are the same. We're canceling them out either by multiplying them or dividing them. And when we go through a series of all that, which through here, what we get left with at the end is this value here. When everything cancels out, we're down to seconds squared per meters, but we need to invert that. So invert that to seconds squared per meter squared, and then we square that, or we do the square root of that to remove the square, which leaves us with just seconds, or I'm sorry, meters and seconds. So after you do all of that, what Maxwell did is he took the square of the sum of the two constants, right? And that gives the speed of light, those values. And after it's inverted and you do the square root of that, it gives you the speed of light. Well, close to the exact measured value. I just rounded up to 300 million meters per second. 299
Wait a second. You're saying that they got to attribute the properties of the vacuum to speed of light itself, and they just say the one doesn't have any properties, but actually speed of light has the same properties? Is that what they just said?
The exact same. So it turns out it turns out that the physical properties of a vacuum that are causing the impedance, that the reciprocal of those properties gives an induction rate of 299,792,458.
That's a doozy of a coincidence for me, guys, I gotta say.
Dude, that's a crazy mathematical relationship to establish, and that is the baseline of all modern physics. Now, whether or not you believe in an exact speed of light or however you want to interpret it, whatever, this relationship and what is measured against this value has actual ratios to real velocities, etc., which is what we're going to cover. But this is just establishing the mathematical relationships in terms of taking the measured vacuum properties that were derived, and also applying some math to it and showing through that there's a relationship there that dictates, that just happens to be the same thing as what is going to be experimentally measured. We get into the experimental measurements here as we continue. But yeah, so just for unit consistency, you reduce everything down just to give like a truncated version of what we just went over. Everything breaks down like this, and then on the last portion, when you convert into reciprocal, you get the speed of light from that. That's what show and we'll continue or show where he on as we continue. What does that mean exactly? Well, like Shane just said, the relationship between electromagnetic propagation and the speed of light in a vacuum based off of the impedance values comes out to be the same. And so what that shows is that this would dictate like the maximum rate in which you could have um, this wavelength propagated, right? So this flux here in the electric and magnetic field is what's going to how fast that occurs is going to dictate like the frequency, right? So this is those values of the vacuum dictate the geometry of what's being propagated. So this is what determines the baseline for electromagnetic propagation to exist to begin with, to have measurable wavelengths and frequencies, because what this is describing is a change in the electric field and a change in the magnetic field. And what did we just learn about? Two specific properties that exist in a vacuum that dictate how fast and how much these values can change.
Yeah, their story's starting to fall apart a little bit.
The magic wore off, right? You look behind the curtain a little bit. I just saw a pimply faced wizard back there. It doesn't look that impressive all of a sudden.
Yep. Let's see. So the wavelength would be the distance here between the peaks and the trough. And then you would have however many cycles it would be how many peaks and troughs exist over the period of time that you're looking at it. And trough here. Ooh, yeah. The frequency is the unit value for that is in 1 second intervals. It's not defined mathematically. It's defaulted to 1 second interval. That'll be in future presentations. And the wavelength and frequency have an inversely proportional relationship. So when they change, they compensate for one another. So if let's say this goes through a medium, right? It's going to the wavelength and frequency are going to change inversely proportional to one another.
So, have you ever seen a diagram or a drawing where it shows the transverse longitudinal waves, say coming off of a radio antenna, where it would, each wave or each, I don't even know what you would call it. This is just kind of almost like a vector, isn't it? It's showing
Direction, magnitude.
But the real thing goes off in all directions like this.
Oh yeah. I know what you're saying.
Field
yeah,
around it. It's not just a nice straight little one line going out. I mean, they are getting better at focusing these things. So maybe it's not heard back here and isn't picked up back here. But a lot of them go off in every direction. So this always kind of fooled me.
Yeah, that's good to know. So this is just a conceptualized, model to interpret and think about these measurements in relation to frequency and wavelength, and in terms of like separation and what these fields are doing, and what this intersection point means here, etc. Right? Because in reality, like Zach was saying, the wave fronts are spherical, like they propagate outwards, like omnidirectionally, pretty much. Yeah, this is just a way to.
I think it's a way to show the orthogonal relationship, right? When you say inversely, it's a way to visually depict what that would do as an offset to the other. I think that's why it's, I think, linked to 1 second intervals, because you see one exact cycle, I think.
Yep.
It's almost like two fields fighting each other, One's going this way, the other's going this way, and they're kind of holding each other right there.
Yeah, so as the magnetic field starts to die down, the electric field will start to pick up, and then as that starts to die down, the magnetic field picks up, and this just goes on in relation to the frequency that it's put out. That but that'll be caused by the modulation where it gets sent out. But anyway, what's really cool though is this intersection point here is like they say that there's nothing here, but this is where the charge potential exists that is going through the ether that is allowing the electric and magnetic fields to induce one another, because the way that they have to interpret it now in mainstream is that there's nothing here at this intersection point, that these fields are just inducing one after another for no reason.
Without any energy started by nothing and continue into perpetuity. It makes perfect sense.
Essentially. Yeah, there's a really great breakdown by a Fractal Woman on YouTube. If you search Anel Denu on her channel, that's IONEL. Search that on her channel. You can watch a really cool video on Anel's conceptualization on electromagnetic propagation and how all that relates with some really good visuals. So we'll continue on now with there's either nothing or something in the vacuum. And we went over the philosophical preface earlier about, you can't say there's nothing, because nothing doesn't have any properties. It doesn't exist. Philosophically bankrupt. So the speed of electromagnetic propagation in a vacuum is the inverse of the square root of the product of the magnetic permeability and permeativity and permeability properties. How crazy is that? So this thing that exists in a vacuum that we're told has no physical properties or meaning or anything like that, or is also dictates the speed of light, and that's actually what's measured.
Look, we've discovered nothing. Nothing just happens to have the exact same signature and as the magnetic and electric permittivity. Yeah, like here you go. We got it.
Was that Ionel? Would it be Dinu?
Yep, DINU.
I'm gonna subscribe to him. Yeah,
Oh, dude, he's awesome.
I will share this for everybody in chat.
If you go to his ResearchGate, he's got like 4 or 5 papers on a new ether theory that it's like a electromagnetic propagation, electrostatics, and some other stuff, magnetism, etc. Dude, they're awesome reads. Highly recommend. You'll love them.
I'm definitely going to check that out. Thank you.
You'll definitely learn all about electrogen. Electrostatic juice.
The juice?
Yeah, the actual juice. All right, cool. So here what we're going to look at is a prediction and model from 1818 proposed by Fresnel to model the density of elastic ether in matter, which is said to be proportional to the refractive index squared. Well, that's a heck of a relationship to establish and propose for the values. And what we have here on the side, this little parentheses here, this 1 minus 1 over n squared, is the Fresnel drag coefficient. So this is going to basically dictate how fast or how much velocity of a moving medium is going to be translated to the speed of light as a function of the refractive index itself. So the more dense the refractive index is, so to speak, the more velocity will be translated, and vice versa for the. So this is an excerpt taken from a modern textbook where they're going over relativistic velocity addition and how it matches previous experiments, primarily the Fazal experiment, which is really interesting because, although this is an old experiment, right, derived in the 1800s, the Fresnel drag coefficient is still accounted for in modern technology like inertial navigation systems, ring laser gyroscopes, etc. Anytime you've ever heard of a gyroscope measuring Earth rotation from like a laboratory or whatever, they always have to account for Fresnel drag in there. Basically, what's happening is the ionization in the electric current that's flowing through the apparatus is causing the gas to flow in a preferred direction, and that medium in motion is actually giving a velocity boost to the light, which is causing an interference in the readings, so the light has to go it's going a little faster and a little slower in proportion to the square of the refractive index for some reason. That's really weird. Why is light being dragged by a material medium? That doesn't make any sense. But anyway,
and they do it so nonchalantly.
So nonchalantly. And then so yeah, what's really funny is Einstein has this whole thing on velocity composition where basically when you add to the speed of light, it always comes out that it's never going to exceed the speed of light. And for this, you just have to use classic velocity composition essentially because it is what it is. So he's just like, here, you have to use this thing where C is always equal to C, no matter if it's plus or minus V. And he's like, by the way, if there's a medium though, classic velocity composition applies. Okay, dude. Thanks,
If there's a medium.
Yeah. Yeah, so these formulas agree within 99.99999999999% of each other. So anyway, we will continue on here because the implication here, so the preface that Fresnel had was that inside of a medium, right, a translucent medium, that the density of ether will be proportional to the square of its refractive index. So there's going to be more ether inside of it, essentially, if the refractive index is higher versus lower. And then this was experimentally verified about 40 years later by Fazal. So we'll get into that, but real quick to show what this relationship looks like on a graph. Suppose this dotted line here is the speed of light in a vacuum. So we're at the Z line here. The red line would be air. So you notice there's not much deviation here. And in other words, the faster the air is moving, it's not gonna change the speed of light by very much, right? But when we have glass and water, now the faster those start moving up to 10,000 miles per hour, right? This is how it's going to affect the relationship in terms of velocity addition and retardation going with or against that medium. So in air, it's pretty much negligible in comparison to a vacuum. This line is pretty much, you're not going to notice any deviation in here between the vacuum and air, really. But what this formula predicts is how these values will change in relationship to the medium, the refractive index of the medium and the velocity that it's traveling. So that's to kind of show the significance of what was predicted there. And then what was actually measured by. So before we get to Fazal, earlier we covered, electromagnetic propagation and the relationship to the electric permittivity and magnetic permeability properties. This was Einstein prefacing that in his 1865 Dynamic Theory of Electromagnetic Fields paper. So this is just going over that where he originally showed that. And then on the Wikipedia here, it shows using the modern formalism for the field equations for electromagnetism, you can also derive the same thing based off of the values for the vacuum constants. Right. And then before we get into aberration, I wanted to show the Fresnel drag thing. So the Fresnel drag that was experimentally measured in, what was that? 1851, right, from a formula from 1818. This is how the experiment went down, using sunlight and a beam splitter, sending the light through a tube that had water flowing through it at 7 kilometers a minute or something like that, 7 kilometers an hour. It ended up translating 44% of the velocity going with and against the water. So 88% total of the velocity of the medium was translated to this fringe pattern here. So in other words, the fringe pattern that would be predicted if there was no medium in here was slightly bigger than, if there was a moving medium in it. And that was actually what was predicted by this equation up here. And then when you measure this out, so how you interpret the fringes, right? Let's go over that real quick, because this is extremely important.
Well, actually, can we go over what a fringe is? Because if people don't understand that there's any sort of measurement of motion, right, then there would be no interference pattern to begin with. So let's back up and say what is a fringe exactly?
Great question. Okay, so let's take a look at this diagram to start off with. So we're starting with the same coherent light source. Now, whether this is sunlight coming in and we're focusing it through a collimator and then it's going through a beam splitter, or if it's from a incandescent lamp, light bulb, laser, doesn't matter, right? As long as it's the same light source, right, starting at the same time, we know it's starting in phase. Now, when it hits the beam splitter, we have a clockwise and counterclockwise beam. Now, when this beam recombines after hitting mirrors that are angled 45 degrees to the original one, we'll hit a beam splitter that's also angled at 45 degrees where it will recombine and hit a canvas. And you can see the fringe pattern on it. Now, what is a fringe pattern? That is the pattern that is created from constructive and destructive interference from waves. So when these started in phase, if they recombine, if the speed of light is isotropic and there's no change, there's no motion, there's nothing to register any change, then when this red and when this red and blue line recombine, I almost said black line. I'm like, there's no, anyway, when these blue and red lines
That's
recombine,
racist.
yeah, when these lines recombine, this whole thing should be illuminated.
So if they recombine perfectly, then what would we infer if there's no interference whatsoever?
Yeah, so if they recombined, and then that would mean that the speed of light going clockwise and counterclockwise is the same, and there's nothing detected. Now, what they actually measure is an overlap. So earlier we looked at the peaks and troughs diagram to help us conceptualize what a wave is. So when we think about that red and blue split beam and these peaks and troughs, well, when these overlap or intersect, they either cancel out or amplify. So what we're looking at here on this diagram, at this black line versus illuminated portion here, we're looking at constructive and destructive interference. So the constructive interference is going to be the white line portion, like the lit up portion, and the destructive is going to be the black portion. That's going to be our fringe. And that's going to be, we can take the wavelength that's of light that we used, and we can add that in the fringes. So it'll be like, so say we predict like 3 fringes, right? Just to make it like easy, right? So instead of having one singular thin black line, right, it'll be the width of 3 of them combined. That makes sense? And the width and the distance of all 3 of those combined, the square of that distance is proportional to the velocity that produced it.
Yeah, I think where people get hung up when they say it's arbitrary is when you decide how much each fringe is going to correspond to how many mph velocity component later. What we're talking about here is ratios in most cases, right? We're literally mapping a ratio. What they later then decide to empirically like measure with the ratio later is kind of arbitrary to the method being, mechanically sound and mathematically sound. The ratio holds every single time, no matter what.
Yeah. Yep, it's an absolute measurement of velocity. So let's see here. Is there anything I wanted to add to that?
Well, real quick, one more.
Yeah.
Sorry, go ahead.
So yeah, when we get into interpreting the fringes, right? I'll actually cover this as we continue with the Michelson-Morley stuff, because they're using the same equations that they derived back then as they are using now in modern technology that is way more precise than anything they had in the 1800s, yet these equations still apply. But anyway, what did you want to add?
I was going to say, if you had to take the position that there was no measurement of motion whatsoever, looking at this data, how would you do it? Because I can't think of a way.
You would just have to deny measurement and repeatable measurement at that, which is the worst kind of thing to deny.
Amen.
All right, so let's see. We were on Fresnel. We skipped ahead a little bit. Maxwell. So astronomy. So mathematical framework. So this is important for a little bit later. We'll cover Airy's failure and Arago and like why Einstein proposed not only removing the mathematical framework of the ether, but also the physical medium. So in relationship to what we're going to be looking over later in some of these equations is a V over C relationship. What does this mean exactly? This is the velocity over the speed of light. So earlier when we looked at that value that was almost 300 million meters per second, we have a velocity here, and we can extrapolate the exact ratio there. And so you can kind of think about that as using light as a reference frame to measure motion against. This is what we're going to be. So when you see an equation that is V over C, now in modern times, obviously it's been co-opted by relativity, and you're going to be looking at it through a Lorentz transformation most likely. So when you see it there, it'll be there won't be an absolute frame or whatever, right? But in classic physics and the Sagnac effect derivation, all that stuff, when we're looking at that, we're looking at classic equations with an implication of an absolute frame, and this is what the motion is going to be measured against. This is what the ratio is going to be measured against. Light in its inertial frame using that constant value. Okay, so this will be important for aberration later, because one of the proofs of heliocentrism is aberration, is the aberration angle, the annual aberration for stellar aberration, they say, right? Which is a V over C relationship. It's it would be an absolute measurement of velocity, right? Now in relativity theory, they say that there's no such thing as an absolute measurement of velocity, yet almost all heliocentrists are relativists or staunch relativists, and they'll actually use this. They'll use the fact that light, when a medium was introduced, to change the speed of light to see which of these things is moving, either the Earth or the sky, to produce this measurement. They actually say that the fact that it didn't change is proof that you can't tell that you're in motion, even though the initial starting point was a measurement of them saying, "Hey, we found motion." That sounded a little hard to follow and a little contradictory. That's because it is, and it's ridiculous.
The problem isn't you; it's the idea.
Yeah,
Okay, all right.
the problem isn't you; it's the framework put forward to break your mind. Okay, so we got a Fazal experiment that closely measured the speed of light. So when we look back here at the Maxwell thing, he mentions 4 experiments here that confirmed the speed, or that get close to the speed of light that he calculated. And these are loose approximations. One from our boy Foucault, and the other 2 from Fazal, and then another one from aberration, using this V over C relationship and backwards deriving what it would have to be to produce it. They came up with about 308 kilometers a second. But anyway, we'll look at the premise for one of those experiments here. So the basic premise was, over like a 5-mile distance, he was shooting a light source at a reflective mirror as he spun a toothed cogwheel at a certain rate, and then measuring the pulse rate in which he was able to observe the light, returning through the cogged wheel. Over a course of 20 minutes, he averaged out what the speed of light would have to be to complete that versus the rotational rate of the apparatus. So there's a cool video of this being reproduced in modern times. I'll link it here in the chat for the lads and ladettes to check out. Not going to play it here for potential copyrights, but it is a cool video. And this was originally done in 1849. And then, of course, he did the follow-up experiment in 51 with the water. How do I get to the next slide? There we go. Okay, so this was his follow-up experiment after having the approximation for the speed of light. So this is where it gets a little interesting, because they have Maxwell's like, hey, I just linked electromagnetism together with the vacuum constants in 1865. But here we have Fazal and Fresnel making predictions that require this absolute value that hadn't even been experimentally measured yet. That requires an exact value for interpretation. And yet they, down to the wavelength caused by the interference pattern, they were able to measure the exactitude of this equation that is still used in modern technology today, that requires way more precision. So that's crazy. Not sure what to make of all that, but they had these values that they're using. Again, these ratios all turn out accordingly. So earlier when I was going over the case of aberration, where they try to use the speed of light and the angle of aberration produced to say that that's substantiation of Earth moving around the sun at 30 kilometers a second. Well, that would require um, the so it requires two things, right? So back then they had their ether model conceptualization was that the ether was static, right? Electromagnetic waves would vibrate and oscillate through it, but the medium itself was static. The difference in our interpretation is that the Earth is stationary and the medium is dynamic. The medium is in motion. So the difference here is that they were trying to do things like measure the Earth's motion through a static medium. So you would still have the mathematical interpretation of motion being relative to the medium using that. And then, like, as a physical medium, their interpretation was that it was static, stationary. So anyway, they were trying to interpret through that framework this angle that they were measuring throughout the year that comes out to a ratio of 30 kilometers a second, because we all know when you complete a triangle, you can complete the other halves of it. You know the other two. So they were like, okay, well, this must mean the Earth is moving. So when they went to do some further experimentation here to substantiate that, one was Arago. I got the wrong citation for that. That was Arago in the 1800s. I think in the 1870s, late 1860s. He put a crystal prism over his telescope, and what he was looking for was when starlight was in the exact center of his telescope, it was supposed to, have to deviate, or it was going to move out a little further than would be normally predicted if the Earth was stationary, because the Earth is, moving out from underneath the light that's being slowed down by the crystal prism. But what he found was that there was no angle change required when the starlight intersected the half point of the telescope where the crystal prism intersected with the air, which is implying that the starlight is already coming in at an angle. If it doesn't require any sort of additional correction, it certainly implies that you're not moving.
Yeah, yeah, that was huge. Once I and that one took me a while to get. I had to see a visual demonstration of it.
Yeah.
Just explaining it to me, for some reason, I couldn't grasp that idea. But yeah, soon, Malcolm Bowden. Have you ever guys seen his channel?
Oh, Malcolm Bowden. Great man.
Yeah, I take that as a yes. And yeah, he does some great visuals and stuff like that in his videos.
Yeah.
I'll try and grab that for the people in chat if they haven't seen him.
Nice. Yeah, and then following Arago's experiment, Airy came along because he heard about a man named Professor Clinkerfuse, who had said that when he filled his telescope with turpentine, that he had to make the additional angle correction that would be required if the Earth was in motion was measured. So Airy was like, no way. Clinkerfuse is a man of repute. Let me see if I can verify this, because I'm all about the scientific method and verifying things and all that stuff, right? So he had a special zenith mount telescope made. So this angle here that looks like this telescope is tilted is actually incorrect. It should be perfectly 90 degrees. But this is just to kind of exaggerate and show, for example, right? But anyway, he had this 90 degree zenith mount telescope with a double bubble level to make sure that he level at the top and at the bottom. He was looking up at a starlight, and he measured normal aberration in air, and then they filled the telescope with water, and he measured pretty much no deviation. And that implies that the light already comes in with a horizontal drift to it, and that the Earth is stationary. There is no mathematical way to predict using the V over C ratio that the speed of light, or that somehow that this angle would remain the same. There is no formula to make that prediction. Now, what you can do is you can't even use relativistic velocity composition, which has to agree with classic velocity composition, meaning how they derived what the angle change would be in the first place based off of the refractive index slowing down the speed of light while the Earth's velocity remains constant. So the angle change is going to be facilitated by the slowing of the speed of light with respect to the, that 30-kilometer velocity of Earth to produce it. So, the only thing that they could do is ignore that, right? And just do a transformation between an observer on the sun and the Earth, right? Because we started with incoming starlight and an observer on Earth. So the original V over C relationship we started with was, observer, starlight. Now they had to. Now they're going to have to take it to, observer on Earth and a observer on the sun, because the Earth is the thing moving around the sun. They say so. The relative motion between them is now going to have to produce is going to be said to be the production of the thing that they're measuring with the V over C relationship initially. But now we're looking at it through the Earth and Sun relationship through transformation. And what we're going to do is, in our frame, because we can't measure the difference, we're going to put it all in the sun frame and say, if we were an observer on the sun looking at a telescope at us, we would see the angle difference change. But, because we're not there, because we're in the frame that's in the relative motion, we're not going to be able to measure it by any perceptible means, even though we started with aberration in air. But just like forget about that and just never bring it up.
That
So anyway, that's how they have to explain that. And this is going to be important because of that V over C relationship and the mathematical implication of the motion being relative to that, and how that works. It was important to go through the whole story of this because, as I stated earlier, right, it's not just a mathematical framework or a medium. It's all of these things. Right?
I guess it's a better excuse than Tyson gave with the add another well, and then you can, at least this one, nobody can check this one. Nobody can go stand on the sun to verify whether they're right or not.
Part of the allure, I'm sure.
Yeah.
Yeah. But hey, you know what does substantiate the correctness of it? If the math works out and it's symmetrical. All right. So to finally put the matter to rest, is the Earth in motion or not? They came up with the Michelson and a wrong citation for this too. This is 1887 on the relative motion of the Earth and luminiferous ether. But anyway, they came up with, so following the interferometer setup that Fresnel used to measure the velocity of light in running water, we have an interferometer that's going to operate in open air, that's going to create a cross-section orthogonal to itself. So we're going to be able to align the interferometer with respect to true north, and then we're going to have an east-west arm alignment, and we're going to be able to rotate the interferometer. We're going to measure variance throughout the day and throughout the directionality that it's aligned to see, what, with respect to true north, where is there variance? Like, is where's the variance in light come from, right? Is it isotropic? Is it anisotropic? How are we going to tell? Well, we're going to rotate this with respect to true north throughout the day and throughout the night, and we're going to measure the minimum and maximum dimensions of the fringes that occur, and then later we're going to plot those out and see if we can do a Fourier analysis and see if there's a sine wave that's created. But we'll get to that in a little bit here. Okay, so we have our interferometer set up. So to kind of give a readout of what this is, we have a light source sending in light through a lens, hits a beam splitter. It gets split orthogonal to itself through mirrors that send it back and forth, where it hits another beam splitter, where it completes this cross. And after completing the cross, it hits another beam splitter that focuses on a canvas and a telescope. So you're basically looking at the I have it on the next slide. Yeah. So we're basically zoomed in looking at this constructive and destructive interference pattern that's created by the phase difference with respect to the north and east-west alignments, right? Like that, and those north-south arms with respect to the east-west arms, we're looking at the separation created by them. Anything else I need to cover?
Whoa, was that a really stark difference between the speed on a north-south vector than an east-west vector? Is that what that showed? That looks substantial.
Yeah, what was their magic they pulled for this one? Because that's way obvious. I mean,
This is where they introduced relativity theory. And said that there's no medium, no mathematical reference frame, none of that. Get rid of it all.
Just
Yep.
It's in the toilet.
But for us, the east-west is the only vector, right? It's an east-west distortion, always, not north-south.
Always east-west.
Of the ether wind. Yep.
So get this. There's no ether, right? There's just relativity theory, all motions relative. Now, the physical displacement phase difference caused now due to the light being constant has to be due to the Earth physically rotating underneath it, right? So if you're on a ball that's physically rotating, you're not only going to have a east-west variance, you're also going to have a north-south variance. Now, that north-south variance will be slight, especially over shorter distances, but definitely perceptible, because if the answer is the speed of light is isotropic in all directions, then you have to compensate for the mirror moving out from the side of the interferometer. That's never accounted for at all. Now, our proposal is when you're traveling perpendicular to the east-west directions, north-south, you're traveling perpendicular to the flow of ether, so you're not going to get a velocity boost, right? Whereas in modern cosmology and physics, north-south variance is mandatory.
Man,
for dynamic reasons.
Hard to set up right here.
Oh, this old thing? Boy, this is just a concrete slab, super polished fine mirrors with 60 what was it? Millimetric screws for adjustments to the mirrors, and
wow, just getting all that lined up.
A giant mercury vat, equidistant spacing for the numbering so we could monitor our deviation with respect to true north. You talking about this old thing?
Man, that's
several collimator. Yeah. Anyway, yeah, it's pretty cool. So let's see here. I think I covered everything for this. So this was to test the concept of the Earth moving through this static ether that we talked about earlier, and how the movement through said ether was going to cause a phase change in the light with respect to the north and the south, or I'm sorry, with respect to the north, south, and the east-west arms. And that phase difference, knowing the relationship that they measured earlier from our boy Fizzy, is that you can measure the square of the distance and phase is proportional to the velocity. Now we're going to take a look at what that means exactly. So here was the Michelson derivation and equation that they used here. The important part to note when we get down to the bottom here is we have 2 times the distance over velocity squared over c squared. And the distance is just the total path length that light has to travel to complete its circuit. And this is all they needed, right? So they knew how to interpret this. They knew what the measurements would be for the fringes. They knew they predicted how much fringes they needed to get the velocity for the ratio, for the fringes measured to be for the predicted value for the ratio that they need for heliocentrism to be true. They knew the exact amounts for everything they needed for that, based on the wavelength of light that they were using, which was yellow light. So anyway, when they go through the measurements here, we have this peak and trough here, and this is with respect to turning the interferometer 360 degrees. So this should be, the dotted line should correspond to 0.05 fringes, which corresponds to 30 kilometers a second. What they measured was just over 1 fringe, which corresponds to about 6 to 8 kilometers a second.
Something's wrong.
Yep, it turns out all motion's relative, and that's it. There's no ether. So they have this measurement. Now, keep in mind the data set that we're given here are scraps taken from a larger data set. And what we're given here, we're not going to be able to extrapolate any sort of like periodicity or anything crazy like that. That would be really cool. But this is just like randomized samples throughout the day on random intervals here. But this was taken
So
from
it
a
was
from a
done
larger
multiple
set.
times. You're saying like
Yeah, this
a
is
lot of times.
yeah, this is the only record that we're given from this. And then at the end here, they propose that they should do it more times throughout the year. But yeah, what we're given here, we're not going to be able to do any like statistical analysis to get any significance out
Mhm.
of this so far, other than magnitude of the measurements themselves in terms of statistical significance, but like finding a pattern for like sidereal, not out of this data set. But what they do, so we cover some important things here at the end of the paper. It covers how much displacement there was versus their predicted amount. So I'll just read the whole thing. The distance was about 11 meters, and the wavelength of light that was used was 2 times 10 to the 7. Hence, the displacement to be expected was 0.004 of a fringe, which is what this graph up here is for 0.05. The actual displacement was certainly less than a 20th part of this, and probably less than a 40th part.
Wow.
But since the displacement is proportional to the square of the velocity, the relative velocity of the Earth to the ether, and is probably less than 1/6 of the Earth's orbital velocity and less than 1/4. So way less than what they had expected, right? 6 to 8 kilometers versus their expected 30 kilometers. And what precedes only the orbital motion of Earth is concerned. In this combination of the motion of the solar system concerned, we know very little about with certainty, and the results would have to be modified. So, like, they're talking about the prediction and all that, and like times of year for measurement to see if they can get the corresponding, velocities, etc. And this would just be a possible resultant velocity at the time of observation was small, although the chances are against it. So he's saying like maybe there's the big boy velocity out there, but we're just in like the little boy pocket stretch or something of the velocity range. And maybe like if we do it later, we'll get that big boy galactic velocity. So
They were hoping, weren't they? They had their fingers crossed. Like maybe if we just do it
yeah,
6 months later.
And this is really important too because there's a specific way to measure and interpret these fringes, right? Now, this velocity and the way that they did it, the way that they measured it, is the same way that they do it right now for the Sagnac effect and inertial navigation systems, etc. So all standards of interpretation are based off of this equation here that they used, right? Although this is for a Michelson style setup, right? A linear interferometer, right? This equation is the same as the Sagnac equation, which we'll get to here in a second, and the significance of this, because what this shows is that there's a correct way to interpret this and make the measurements, right? Now, in modern times, when people are searching for that galactic velocity, they will say things like, "Oh, well, you know what? Michelson had it wrong, and what we need to do is, you know, basically extend the gap a little bit, combine these fringes, reinterpret how we're going to measure this, and this will give us that delicious galactic velocity when we do that." Now, the reason people think that they have the freedom to do that is because this setup, right? This cross, they call it an orthogonal setup when it's going perpendicular to itself, the light beam. They call this like the Michelson style interferometer. They say in mainstream that this is a special interferometer that detects linear motion, and it can't do that because relativity and all motion, blah blah blah, right? But if we have a closed loop, we're all good to go. If this were if this were a square, a solid square instead of a cross, then it would be a different type of interferometer, they say. So they feel like they have the freedom to reinterpret those fringes because in the modern mainstream, the way that they interpret is a little different for angular displacement because they don't want to be associated with they don't want people to to be like, hey, you can actually square that and it'll give you the linear velocity too. Do you know that? Like they don't want you to know that. So we're going to go over the slightly different interpretation of how they take the readings now. but still same relationship, just different way of plotting out the minimum and maximum peaks instead of
Do
looking at.
they
Yeah, go ahead.
address any of this with a mechanical gyroscope?
No.
Like they don't even touch on it, do they?
Yeah.
I've got all kinds of little article snippets from way back when saying, hey, why isn't my gyroscope drifting? These were from, the scientists of the time saying
Yeah.
saying that it's bearing drag or this is not an adequate enough answer. There should be a gyroscope somewhere in the world that's built, well enough that it's going to pick up the motion of the earth. Where is this thing?
Where do you exist at? But yeah. So no, we're just talking optical, like light stuff for these. So let's see here. So he suggested that the experiment be replicated at different times of month, just because the Earth and their model will be traveling at different speeds as it's perihelion and aphelion. So he's like, maybe we should look for variance, something like that. Anyway, these measurements are too large to be explained by the theories that were put forward to explain the previous measurements for the aberration angle not changing when they added water, for example. And those theories were, relative transformation, etc. Right? So they actually had to round this down to 0 and just say that it measured nothing. So the modern interpretation, while we're looking at this measurement of just over a fringe, we're looking at our boy talk about how much the velocity that corresponds to, which comes out to be 6 to 8 kilometers a second. We're looking at all that. And the modern interpretation is that that's actually 0.
That seems to be like what they did with reinterpreting Mickelson and Morley as a null. Well, actually, the null means not what we wanted, not 0. No. 0 would mean that we have velocity and we measured no velocity, so therefore we resulted in a null. It's like, what kind of linguistic nonsense are you talking about?
Crazy. All right, so now we get into Sagnac in so that was 1887, right? Now we have Sagnac in 1913, who, using the same equation that is derived here, which we'll go over here in a second. This is just the modern formalism of it. Sagnac's looks a little sloppier, but it's the same when it's reduced down. What we have here is, now remember, if the light beam goes in across at a right angle to itself, that's the bad interferometer that can't detect anything because relativity is super true. But when we have a closed loop, we can detect rotation. Now, what happens is, when this is spinning, it'll be out of phase proportional to the velocity clockwise, and it'll be retarded proportional going counterclockwise to the rotation. So when it recombines, there will be a displacement. Now, what they do, instead of looking at that square relationship and the distance in the phases, they plot the peaks in the versus the difference of what it should be when it's not moving or whatever. So they're plotting like minimum and maximum peaks to get the angular displacement. So when they want you to look at this in terms of rotation rate, like radians, instead of a translational velocity, like it's rotating at 7 kilometers a second, they want you to be like, oh yeah, it's rotating at 3 degrees an hour instead, because if they have to associate a velocity with this interferometer, they're going to have to explain this bad boy. They can't do that. So this has to become a separate mythology within the framework. This is the special interferometer that can't measure or anything. So we go over quickly here the classical explanation that provides an explanation for the actual measurement, right? The actual, when this system is in motion, right? When it's dynamically moving and the measurement is taken with respect to absolute space, there's a phase difference measured. And that's described by a mathematical relationship where the timing difference is described with respect to the clockwise and counterclockwise velocities. To produce that timing difference based off of the change, which is the change in the path length, which starts us off with the area that light has to propagate with. This is all part of the equation to derive all this. So when it changes with respect to absolute space, this predicts how much that change will be. So this is what you would call a dynamic equation, right? It describes motion with respect to a stationary frame down to the wavelength of precision. And then, of course, we have the same equation, or I'm sorry, an attempt to derive the same solution using relativistic postulates, which are strictly kinematics, right? That relative motion is true, right? Whereas this equation is with respect to a stationary frame. So using the kinematic postulates that there is no frame for this motion to be relative to, and the light will simply complete its circuit irrespective of the path length change, because there's no motion, there's nothing for this timing difference to be relative to because of the path length change. So what happens is they predict no change. They predict no fringe using kinematics. So if you were to break this down into like a kinematic and dynamics situation, one of these equations would be best described as dynamic. The other one would be described as actual kinematics, since relativity is based on kinematic postulates, relative motion.
So there's motion, but the relativist seeks to say actually arbitrarily there is no motion because all frames are equal, therefore you can't tell what's in motion. And the actual observable truth is all motion is relative to the stationary Earth frame, therefore there's motion relative to stationary Earth.
All the laws of physics and all dynamic predictions are with respect to a stationary Earth.
Crazy. So why would people fight so hard against that position? I wonder if it's based in deep rooted in some philosophical framework that disagrees with the results of this. I don't know. I'm just speculating wildly, and that's just my opinion.
Possibly. All right. So shout out to the lads who made sidereal measurements. So going back to the Michelson-Morley style interferometer, not to be confused with the closed loop circuit that we looked at earlier, but we're going back to the cross, that right angle interferometer. The experiments were picked up by Dayton Miller from 1905 to 1930. And then they were repeated by Hector Minera in 2002 to 2004, I think it was. Or was it 2001 to 2004? And then anyway, he published in 2006. He left his interferometer running for 3 years straight, took measurements every day. And this is Yuri.
Awesome, dude. Just shout out, man.
Too, right? And this is Yuri
Mad
Galev
respect.
at the end, who did a series of interferometer experiments, one using radio wave interferometry, radio wave interferometry, and the other using optical wave bands, so just the classical laser interferometer. And what was that? 2001 to 2002. So yeah, back to back. So Miller did his measurements in Cleveland and in California in Mount Wilson at the observatory there. Minera did his in somewhere in South America, can't recall. And then Galev did his in Kharkov in Ukraine. So we have 3 different data points, 3 different locations on Earth, years and years and years, decades apart, right? And they're all confirming the same measurements. Now, when an interferometer is closed loop, no one disputes that it's measuring what they call Earth rotation, right? But measurement alone cannot tell you if the Earth is in rotation or not. Now, we learned this earlier from the Ares experiment. When they got the aberration angle, everyone was super excited because that ratio gives 30 kilometers a second, but they all knew that measurement alone can't tell you if you're actually in motion, and you would have to introduce a dynamic asymmetry into the system, right? What does that mean exactly? They have to manipulate the independent variables, right? They have to change some variables around, right? So when they introduced water, right, the significance of that was, oh, now we can tell which one's moving. It already comes in at an angle, because if we were moving, the angle would be bigger. The only way it could be the same is if we're stationary. So in the same respect, we all have, there's continued measurements, right, with closed loop interferometers that when you plot the peaks, the fluctuations of the speed of light throughout the day, right, when you do a Fourier analysis on that, it makes a sine wave. So when they get that sine wave, they're like, oh, dude, that corresponds to 15 degrees per hour. That corresponds to what we think is producing the rotation of the sky, right? That's what they think they're measuring. Because when they plot the peaks of the measurements, the minimum and maximums against sidereal time, it makes a sine wave. Not when they square the distance relationship between the fringes or anything like that. Just when they plot the minimum and maximums throughout the day. It shows a relationship to sidereal time through mathematical analysis. So
I wonder if their altitude difference could be valued into them.
Ooh, great question. If you're a mainstream globularist / relativist, the answer is no. If you're a etherist, a theorist,
Ether cosmologist.
if you're an ether cosmologist, this is not a problem for you. It's actually a prediction that as you get closer to the source of motion, it's going to be an increase in velocity. So
Yes. Closer to the vortex goes faster.
So here we have closed loop interferometer, starting with Michelson Gale Pearson. We got Doug Marmay from YouTube. Shout out to him, who built his own interferometer, measured sidereal rotation. We have the boys from Stedman and Bilger, who measured sidereal rotation in the south, which is, by the way, non-reciprocal to the north, meaning it wasn't the same velocity. Oh, dude, if you're on a spinning ball, Shane, doesn't the velocity have to be symmetrical in the north and the
By
south?
latitude, it would have to be synonymous with the same corresponding northern latitude symmetry. Otherwise, what kind of a ball is that, dude?
Oops. So anyway, there's a non-reciprocal phenomenon that's happening, which is an interesting way of saying that it wasn't symmetrical in the south, like it should be in the north, like from this Michelson Gale Pearson experiment that was done in the north. And then, of course, we have Bob from Thanks Bob. We all remember thanking Bob, right? So all of these sidereal measurements, what are they measuring? Are they measuring ball rotate or are they measuring sky rotate?
Real quick, do you know if the outer ones were slower than the inner ones, was it? The southern one was slower or faster than the northern?
The outer one was faster.
Okay.
Interesting, huh? With the
Mhm.
relationship of the velocity there. So if you're closer, we'll have to come back to that. So if the vortex north pole, you get closer, would be slower. Higher at altitude. Faster. Interesting. Yeah, we'll have to revisit that.
Mm-hmm.
But yeah, we just got just looked into the non-reciprocal measurements and what they were implying there with those. And yeah, so there were several of these. There was actually two more that need to be added. But yeah, so what are these people measuring, right? Are they measuring, did we all measure ball? Are we measuring ball, or are we measuring sidereal time, right? Because ball spin is a different time. When you plot ball spin against the minimum and maximum, what's ball spin? Ball spin is like 29 or 24 hours and 59 minutes or something like that. Right? When you plot it against that time, it doesn't make the sine wave. So it only makes a sine wave with respect to the stars. And it increases in elevation as you get further away from the Earth, which is definitely not a prediction of mainstream globularity in physics, especially if you're a relativist.
So in its present form, such a measurement would lend itself to exclusively one model and not the other, you're saying, Alan? Or are you saying lightly not that?
Well, if you're an ether cosmologist, like I said, it has its benefits. So
This would be a model exclusive measurement at this point until such a model exists that swoops up that specific empirical measurement.
yeah. And then so real quick to give a further analogy on the medium in which we exist in, right? That fluid medium that is producing these measurements, right? That's dictating electromagnetic waves, how we're able to use them, and how we're able to make measurements of velocity with respect to them, right? This is taken from Ruyong Wang's GPS paper from 2000, re-examining the two principles of special relativity and the Sagnac effect using the GPS range measurement equation. Now, this is really important to note because what we're doing here is we're just taking the absolute value of the time from when the signal was received and the time from when the signal was sent. And that's going to be equal to the speed of light times the time signal sent and received, or minus the time it was received. Now, it looks on the face of it that that's not a C plus or minus V relationship. But what we're going to find out is that this explicitly describes C plus or minus V, and you can actually even use the range measurement equation to derive the Sagnac effect, which Ruyong Wang does later in the paper. But for the purposes here, we're just going to go over his analogy first. Let's see. So he says some people think that the range measurement equation is based on the constancy of the speed of light. On the surface, this may appear to be true. C, the speed of light, is the only velocity term that appears in the equation. Expressions such as C plus or minus V, which are often seen in discussions of special relativity and classic physics, do not exist in this equation. Therefore, some people would conclude that if this equation is correct, special relativity is correct, and that if the equation has been proved with a high degree of accuracy, then so must special relativity. And he goes on to talk about how that the difference in the speed of light has been confirmed by 5 times 10 to the minus 9. So therefore, special relativity must be the most accurate thing ever produced in the world, right? Shane, I see you over there giggling.
No, not me.
Someone in chat wanted to know where's the important text on the screen right now.
Definitely not me. Somebody.
Oh, respect. The most important part is in orange. All I'll say. In red. Green and yellow are just for funsies.
You took that well.
All right, continue.
All right. We should not judge things by their appearance. Right, Shane? Right, Shane?
Or the highlighter color, regardless of how gay it looks.
We must try to grasp their essence. If we analyze the implication of the range measurement equation carefully, we will find that contrary to what appearance tells us about the highlighting situation, that it's really actually super cool. And some people think that the correctness of GPS is range measurement. That's crazy that Wang said that. And some people think that the correctness of the range measurement equation actually leads to the incorrectness of the principle of the constancy of the speed of light, showing that relativity is not correct. Now, this is the actual important part noted in orange here.
This is how we affect change. I get you to see it yourself. I can't just make fun of you. I had to get you to laugh at it too.
All right, this may seem unexpected, but it's quite understandable if compared with sonar systems. Sonar, you say? A system that's used in a medium that uses waves to measure distances based off of timing. Tell me more, sonar system. Recall that in underwater navigation, sonar uses the same range measurement equation in a reference frame based on water to calculate the distance traveled by sound, even though the sound receiver is moving relative to the water. The difference is that the speed of sound in water, A, is used instead of the speed of light vacuum, which is C. However, No one would emphasize the constancy of the speed of sound, and contrarily, everyone thinks that the speed of sound is dependent on the motion of the receiver. All right. So, if there's a medium and you're using that as a reference point to set the speed of light for your wave that you're using to measure, or for the wave that you're using, to measure the timing difference to derive velocity and distance with, then would the exact analogous situation be if there was a system that did the exact same thing using electromagnetic propagation? Wouldn't the direct implication be that we are in a medium as well?
Yeah. Yeah. Like this one is based on this medium. So if you're going to use it out there, you would think out there also has to have a medium.
Yeah. And then so in the paper on the left here, this is pointed out by, what's that gentleman's name? Can't remember. Oh, Daniel Garzi in 2000, on a analysis of the photon in special relativity, points out some GPS operations that are contrary to special relativity's postulates, primarily that first order timing corrections have to be made on the record keeping end of GPS to make it appear that the speed of light is actually constant, even though what we just learned is that the range measurement equation is explicitly deriving distance and location for people based off of accounting for the difference in the speed of light that's proportional to their velocity. You know, as if the one way speed of light is, measuring c plus or minus v relative to you moving towards or against the light, the signal. So anyway, that's go ahead.
And it's also double proving relativity, as it only does one way, even though that doesn't make any sense.
Right. And you'll notice they don't use a Lorentz transformation or anything like that to calculate this. This is just a classical equation, which later Wang uses to derive the Segnig effect. So it's literally c plus or minus v in this equation as he's saying. So that is the full presentation. So we have applicable technology that works on the basis of, a fluid medium. We have interferometric measurements of velocity that correspond to that medium being in motion, as there's no velocity value that's been measured that corresponds to any cosmological values that are necessitated for modern mainstream. The only way to interpret these measurements is with the alpha model, which is proposed by Bennett, right? An absolute lab frame and flexible ether.
Flexible ether.
Yep, the dynamic ether.
See, I still see all of this as just, if you just take away space and make it all a lot more like right here, then none of this stuff even needs to be argued about, really.
Oh, if you didn't have a philosophical bias to object to you being at the center, then when you were to look out and see that indeed you're at the center and everything is rotating around you, your
You gotta
math
come up
wouldn't
with some, yeah.
your math wouldn't reflect the ridiculousness of trying to misinterpret that. You would be just, oh, there are basic forces, Coriolis, centrifugal, inertial, Euler. Oh my God, look, everything's rotating around me. When I mathematically describe it, that's how it works. Instead, they're met with the, well, let me invert everything I see so I can input it into a coordinate system via translation and non-loss to a heliocentric coordinate so I can be more comfortable with the measurements that I'm taking. What?
The classic bait and switch.
Yeah, it's a religion.
So
a one world religion at that.
Yeah, if anyone has a cosmological belief and they're looking for a velocity component, that can get you some velocity, but it's going to be an exact amount. You can't lie about it or transform into a different reference frame and say that it's more than it is.
I could lend you some.
Those are the only stipulations.
Well, that was an awesome Prezi there, Al.
Thank you, sir. Yeah, we will be using it to continue on and build the baseline for future Prezi. So, quick recap of what we covered, right? It was null hypothesis. Ether does exist, or sorry, null hypothesis. The ether does not exist. Hypothesis, the ether does exist. I would say that we falsified our null hypothesis, right? If vacuum properties are empty and nothing exists, then there can't be anything in there causing impedance. Well, that's not the case. So on the face of it, it's already not off to a good start for our nully. But what we learned about was the framework of interpretation and what that means in terms of a reference frame as well for the mathematical aspect of it, and how it is a physical medium with actual physical measurable properties.
I always give this analogy when I'm talking about the ether. For those people that have a hard time wrapping their minds around a lot of these big, scientific words that we're hearing on the show today. I know to you guys, a lot of them, we've been doing this for so long and been studying it, it's kind of like we've learned a different language almost. So to put it into layman's terms, I like to say that the ether, think of a painting. It might be a stream with some, grass, some flowers, some trees, maybe some buildings, whatever you want to make your painting. Now, all those different paints are put on there, and that's the reality of that painting. That's the physical world of that painting. But underneath that is a canvas. And without that canvas, none of that stuff holds together. The painting doesn't exist. So the ether is the canvas. You never get to actually see it. The painting's covered. There's no way of seeing it, but it has to be there. For these certain things to take place and for all that stuff to be there, there has to be something back there holding it all together.
No, that's such a great way to phrase it. It's very simple and easy to understand, very intuitive.
Yeah, it's just,
Yeah, I
and
mean,
the scientific ones will get what Alan and Shane are saying. Yeah, dang, you guys are smart. This is awesome. This was well needed addition, you guys taking over GLOBEBUSTERS. So thank you both so much.
Thank you, sir. We're honored to be here.
honored every week, man. But, so if there are measurements of motion, I know the previous iteration and generation were resistant to measurements of motion because as a flat earther, the Earth is not in motion. So measurements of motion, get away, right? I don't want to see those. No. Look deeper at the measurements, see what they're covering, see where they're coming from, see how long they've been measured, see what the tools are they're using to interpret the measurements, and then you can reinterpret those measurements as proof for our model, right? There is no way for a uniform rotating sphere to cause currently as the current model, right? For them to incorporate the current empirical measurements of motion. It just does not work. Right? So either they can come up with an ether globe model where that would interpret a varying velocity component at the same latitude, or they can currently just say that doesn't fit their model and these measurements only fit our model currently. So super important, I think, to not ignore evidence that could help support your position.
Yeah. Well said, Shane.
Yeah. Yeah, I didn't get into this with the mentality of oh, you know what explains this? The ether for sure. It was very backwards. It started off with hammering out all the relativity stuff, and then interferometry was kind of last because it was the scariest complex subject, and plus it was surrounded by Bob measuring Earth ball rotate. So I was shoot, don't want to accidentally rotate the old ball or whatever. So looking into it, it was that was hard to it was hard to figure out what was going on, but then it became super easy because once I got to the Sagnac effect, mainstream they were well, it could really be anything. It could be this, could be that. I'm like, oh, they don't know either. And then that led me back to well, what was it originally? What did Sagnac think it was? And it was optical vortex. What? There's an ether vortex. Yeah. So going through the history of it, took me back to how to make sense of the measurements, and the big problem seemed to be them trying to cram the philosophical belief system that the Earth is in motion into the measurements. If you could get Earth's velocity into your measurement, I mean, dude, you were gonna be the king, right? But nobody could do it, so they had to make Einstein king. They had to just make a fake king. They were like, "Here, random guy at the patent office. Do you want to be king?" He was like, "Yeah, sure. Sounds dope. I just
Okay.
work here at the patent office. You want me to be the sole proof that the Earth is in motion by asserting that you can't feel it, and that's what motion would feel like? All right, sign me up."
And they were so hardcore to find that measurement of elusive Earth's motion that when Bob measured not that, they were like, "Yeah, we got it. Frame him. Frame it. I don't care what it says. I don't care. No, just put it up there. Everyone just keep saying thanks, Bob. It'll catch on." Right. So like that's how they got it. They just propagandized the results and repeat. No one actually thought, what does it mean? Like anyone who says thanks, Bob, as a Glober, I bet you couldn't spell interferometry, let alone understand the implications of said measurements empirically, dynamically, or otherwise.
Dude, it's so easy to just be like, "Thank you, Bob," though. It's a
Hey,
nice little layup.
and
Like
then say nothing else, throw the little gif up, dude, and be done. As a Glober, you win.
if you believe in ball rotate, but you've never felt it or like looked into it, but you're pretty sure that it's rotating, right? And you turn on your TV and you see that a flat earther measured ball rotate. Dude, you never need to look into ball rotate again. Like you are set, dog. Like, oh, dude, somebody believes something different and actually measured the thing that I believe in, but don't know anything about. Thank God, dude. Thank God I don't believe in anything different. That would have been so embarrassing if I was like, "Hey, you know what, guys? It's looking a little stationary around here." like, what are you, a flat earther? Did you know some guy once thought that and he actually measured ball rotate?
That's what that became, and they had to meme it because otherwise, if they had let him look at the results, I think would immediately analyze it and been like, "Oh, look at this! It's called the ether wind or the ether drag, and it's been measured since 1888. And there's 68 other experiments of other people writing papers measuring the same thing, doing different interpretations. Oh, I'm not alone. There we go. What is this? The proper scientific framework to interpret these results. Amazing, and they couldn't have that, right? So." Thanks, Bob, is what it became, and nobody looked any further.
No.
Yeah, we took it back though.
No need to.
That's the effort, right? To get people to take it back. But to get that to happen, people need a deeper understanding of the thing, the event, the measurement, and the framework from which to interpret it, right? So that's what we're trying to do today, I think, is to provide people the tools with which to properly interpret the good old thanks, Bob.
It'd be nice to do it again. To get a hold of somebody. If you guys know anybody out there with one of these expensive, people call them tools, I call them toys.
Nah, dude, we'll build our own. That dude on YouTube built his own for like $1,000 with copper pipes.
Yeah, we need to get back out there to Colorado and go way up on the mountain and then go way down the mountain and on the same latitude and recreate it again. Because I haven't heard of anybody else doing that. I bet there's a couple of them out there, some physicists.
Oh, yeah.
That had one sitting around.
So
they tried it.
That's what Galev did, and the other guy, Miller. When they went to altitude with their interferometers, they measured a variance.
Like super hard measure. Dayton Miller, particularly 5,200,000 different corroborative measurements across different types of parameters over I don't know how many different months. And then Galev did I don't know how many different measurements. It's always been confirmed. I mean, we could confirm it as well for ourselves, but we were just talking to Eric about what it would take to build a Michelson-Morley interferometer.
Mm-hmm. Maybe one of these days. That's a serious machine to build. Get it all lined up perfect and everything.
Man, what I don't get is someone's doing it with a prism and a light through a window in 1700. Dude figured it all out. Like, what? Same thing, same principle. Dude had it. It blows my mind still.
All right, so we're going to wrap up here. Check out the chats. So Liz, the Iron Maiden, says, looking forward to seeing Cami, Zack, and Jaren again soon.
can't wait till you get here, ma'am. Liz is coming to visit from Scotland again.
Nice.
We might not let her leave. We're not sure yet.
Nice. Second best Bob says, "Can I be seen in here?" With a special preface on seen.
Yes, you can, Bob.
Thank you very much for the super chats. Much appreciated.
Yep, excellent presentation, excellent topic. Well done.
We're going to be expanding more on this Thursday, GLOBEBUSTERS Tech Show. Like I said, if you
Nice.
guys are free and you feel like jumping in, even if it's just for a little bit, whatever, you guys are always more than welcome. You know that.
Awesome, dude. Yeah, we'll likely be there.
Awesome.
Nice.
Add some ethereal dynamics or whatever.
I mean, you had me at
As the
Ether,
kids.
so.
Awesome. Shane, what do you got coming up this week, sir?
Nothing. What are we doing Tuesday?
Tuesday. Well, Ether Prezi on Ether Physics Part 2.
Oh, okay. All right. That'll work. That makes sense. That'll fill in nicely.
Yeah. I don't know.
So then that's what I got going on. Eventually, though, we should do addressing Jaren's globe proofs thing, I think, over here at some point.
Oh, that's next week for this.
All right. So
that's our next week's globe.
Right, which from this week now is now next week, right? When stuff coming up. So we got Tuesday, Wednesday, or whatever, Thursday, GLOBEBUSTERS again.
Yep.
And then Sunday we'll be back.
Nice. All right. Well, that is Shane's schedule is coincidentally my schedule. So I'll see you guys again on Thursday, Tuesday, and Sunday.
It sucks because you always do these at night, and I have to get up at 4:30 in the morning the next day on every next to those days. Just stay up all night.
Just quit your job and or obligations.
Dude, I get up at 4:30 too. I don't partake in the late night. I go to bed at like 9:30.
Yeah, I try.
All right, lads and ladettes. See you next week and or on
Take care,
Tuesday.
all.
Thanks, everyone.